without using the calculator. And then this one here, we are going to apply the CR equations to find the differentiability and analyticity of this complex function. Right? So look at this one here. So very standard form, right? Clearly this one here again, change to exponential function. And then log exponential here, cancel out. Then you just have a simple complex number there, yeah, in rectangular form. And then this is the exponential form, which is a constant. That in fact is a constant, right? That in fact is a constant. So bring this one over to the right hand side. You have this here and divide by 2, yeah? And this term here essentially equal to what? Using Euler's identity, expressed in polar form is equal to given by this. So this and then cancels out. So straight away you get y to the power 4 is equals to 1. Yeah? Y to the power 4 is equal to 1. So where are the values of y? So to solve this one here, you know that you need to represent this one here by polar representation, right? So it is only through the polar representations you possibly have the multiple value representation, but you only wanted the 4 principal one because the others are a repeat of this 4 principal one when you represent them in the polar form. And I have given you a general way to treat this one, right? Including the case, this need not be 1, it can be any value. As long as I can represent this value here in polar form, then I will be able to come up with the multiple values for the y easily. Yeah. So this one here, you are given this complex function, right? So you have to write them into the real part and imaginary part, right? Real part and imaginary part of this function here. So one question that you need to ask, how should you represent your z? How should you represent your z? This is already the exponential function. This is also the exponential functions. So do you want to represent your z in polar form? Polar form is the exponential form, right? Which is, if you represent them in the polar form, sorry. Okay, so if you represent it in the polar form, you will replace the z by r e I theta, right? So now you have exponential to the power of another exponential function, including this r here. Of course, clearly it's something that is going to be quite complicated, right? So this one is definitely out. So what you can do is to choose this representation for your z. Of course, still quite complicated, but we do that. So replace the z by x plus iy, replacing the z conjugate by x minus iy, right? Because with this z here, then z conjugate will be equal to x minus iy. Okay, then you decide what to do. Okay, let us look at this part here, right? E to the power ix minus I squared, so become minus I squared become plus 1 y, right? So this whole term here will become e to the power of y minus ix, y minus ix. So what you do is, this one here is only the real part. Then only leaving this one here in the exponential function. And likewise for the imaginary part here, you simplify into this. Bring this I inside here. So you have ix, then I times minus iy becomes plus y. Yeah, so you have ix here. This is minus ix. So real part here still retained. Yeah, we have not operated this. We have not applied this one yet. We have also not applied the imaginary part. Okay, because here, what is the real part of this? We don't know yet. What's the imaginary part of this? We don't know yet, right? So the way to find out real part, I apply the Euler's identity to this part. This one no need. This is a real part. This is a real part already. Yeah. So I need to apply this to this. So applies the Euler's identity. E to the power minus ix is what? Is cosine of minus x plus I sine of minus x. Yeah, so you get this cosine of x, cosine of minus x, cosine of x, sine of minus x is minus sine x. So this one change to this. And this one here change to this. Yeah. Okay, now multiply this into here, you get the real part. Multiply this into here, you get the imaginary part. And you only wanted the real part. So the real part of this whole function here, the real part of this function here is EY times cosine x. Yeah, then we look at here. I wanted the imaginary part. The imaginary part is only coming from this real term times the imaginary part, which is minus EY times sine x. So minus EY times sine x, and then we still have the item here. Yeah, the item is still here. Okay, this I come from here. Okay, it is not the imaginary part. Yeah, it's not this imaginary part here. It's coming from I here, A to here. So this now becomes the real part with the minus sign, and here becomes the imaginary part. Okay, so this is how you work out the real part and imaginary part. And then what do you do? What do you do? You have to perform 4 partial derivative, right? 4 partial derivative. Then you invoke the CR equation. You invoke the CR equation to determine what? Okay, this concept make it very clear. You apply the CR equation, set up the 4 differential equations, and then equate them according to the CR equation. Then you want to find the conditions. Find the conditions under which the CR equations are satisfied. You want to find the conditions under which the 2 CR equations are satisfied. Right? So those conditions under which the CR equations are satisfied implies that the complex function is differentiable. Differentiable, right? Differentiable. So be very clear, huh? CR equation gives conditions on differentiability. Differentiability of the complex function. It has nothing to do with analyticity yet. So CR equation gives conditions on differentiability of the complex function. It gives the conditions on the range of x and y in this case, and of course in this case the range of z, the complex number, yeah, under which it is differentiable. Yeah. So first of all, with CR equation you establish differentiability, and of course that allows you to identify the conditions on x and y or conditions on z under which you get a differentiable f of z. Then you look into the condition where it is differentiable, and you check for each point that it is differentiable, can we identify that a small neighborhood of that point is also differentiable? If it is, then this function is analytic. Right? This function is analytic. So from this one here, to get analyticity, you need to impose the conditions of neighborhood, right? Neighborhood. To get analyticity, right? Okay, very clear. I hope you have this kind of concept sorted out, because based on the simple quiz, I still noted that many students, still many students are not able to get this concept right. You apply CR equations already talk about analyticity. No. Okay, CR equations give you conditions on differentiability. And then to check analyticity here, you need to check the neighborhood of every point where it's differentiable. Can you identify a small neighborhood at every point that is also differentiable? If yes, yes, then analytic. If not, no. All right. Okay. So clear, everyone clear on this point? Anyone still have doubts, especially those who have gone through the quiz, and on this part here, I've written clearly, this is what you should do. All right, don't jump straight away to check analyticity. You cannot do that. Right? To check differentiability, you apply CR equations and find the condition under which they are differentiable. Only then you can check about analyticity. Okay. So with that done, let us look at this one here. The questions appears in 1819. Right. Again, you're asked to comment on the differentiability and analyticity of this function here. Okay. And then this one here, as I said, it's a very interesting question, very nice question here. So this one has to do with integrations of this complex function, right? So essentially what you would like to do is to make use of the result of the first part. Essentially to say that this one here is analytic. This one is analytic. Hence, you make use of the result of that part to come up with an easier working for this. Even that you still need to understand how to apply it. Yeah. So in this case, we are going to apply the CIF formula. Okay. So this is difficult because this is cosine squared. So it's not a simple way to come up with the real part and the imaginary part. Even if you replace z by x plus iy here, when you cosine of x plus cosine square x plus iy, not easy, right? Even if you replace it by polar form, you also have a difficulty. So I need to come up with an alternative representation for cosine squared. So first of all, I know cosine. Clear. Cosine is represented by this, right? According to the Euler's formula. How do I get this? I've explained that, right? Earlier on, I've explained that Eiz is equal to cosine z plus I sine z, right? So e to the power minus Iz would then equal to cosine z minus I sine z. So if you add these two together, this term will disappear. I will get 2 cosine z. So 2 cosine z will be equal to this plus this. So cosine z will be this plus this, everything divided by half, by 2. Right? You get cosine z is this. Now I wanted cosine square z. So I square this. I don't square this part here. This is no use. I cannot use this function here. So I will square it on the right hand side to get this. To get this. So now instead of cosine square z, I now have a simpler exponential function. I have a simple exponential function now to represent my cosine square z. Okay, so even that, instead of looking at this, I look at here. I still need to decide how to represent my z. So again, look at here, this is an exponential function. So clearly, it is not advisable to represent a z in terms of polar form. So the alternative is to use the rectangular representation. So we apply the rectangular representation, the z replaced by x plus iy, z replaced by x plus iy. Yeah? Then we look into this term here. Yeah? So clearly, I2x times x becomes I2x. Right? I2 times iy become minus 2y. Minus 2y is a real number, so I can take it out here. Right? This one is what? This one here, I skip one step. This one is e to the power I2x. Right? E to the power I2x for this. Okay? So this one will give you this term here. Right? So I don't want I2x because I cannot identify the real part and imaginary part here. So the only way to do that is to represent this in terms of the rectangular representation using the Euler's identity. Yeah. So I have real part, I have imaginary part here. And likewise, I do it over here. This term here, same thing, same concept. So minus I2 times iy becomes plus 2y. That's why plus 2y. Yeah. And then we are left with what? E to the power of minus I2x. E to the power minus I2x in terms of rectangular representation, this is a polar representation, will then give you cosine 2x minus I sine 2x. And 2 is 2. Yeah, just a constant. So no problem with that. Okay. So from here, I will group all the real part together. and I will go group all the imaginary part together, I will get this. Right, so this becomes my V, this becomes my U. U in terms of X and Y, V also in terms of X and Y. Then what you do is, again, establish the 4 partial derivative, and then use the CR equation to see whether the 4 partial derivative can satisfy the 2 CR equations. Yeah, whether the 4 partial derivative will satisfy the 2 CR equations. And it turns out that it satisfies exactly for all values of X and Y. For all values of X and Y. So in this case, this function must be differentiable everywhere. Differentiable everywhere. So if it's differentiable everywhere, it must also be analytic everywhere. Why? Because for every point that is differentiable, a small neighborhood of that point is also differentiable for every point in the complex plane. So once it's differentiable everywhere, it must be analytic everywhere. That is very important for the second part, solve by hands. In fact, there is always some hint that you can look from the question the way you ask, hands or otherwise. So I would say, I wouldn't say 100%. Yeah, I would say more than 90% of the case is to use the hands, because the hint is very clear. Make use of the result that you derived from the earlier part. Okay, and how to use the hands? We exploit the fact that f of z is analytic. Analytic. Okay, analytic everywhere. It's analytic everywhere. Okay, so in this case, I'm going to do the integration on this contour, right? C2. But this is the contour integration. You cannot use a CIF. Cannot use a CIF. Now, and I can, of course, parameterize this contour and then do the integration for the complex number. You can, but it's going to be complicated because over here, the 2 parameters are related. This is a certain slope here, right? It's not a straight line, not vertical line, not straight line. So these 2 parameters are related in the integration. So if you want to carry out integration, some of you will have the difficulty because you may need to use the integration by parts formula. So we think of a simple way out. Okay, with this contour here, I want to construct a closed contour. I want to construct a closed contour. Yeah, so this will be the simpler closed contour, right? C1 and C3. Why I do that? Because along this contour here, only 1 parameter change, right? This one here also 1 parameter change. So integration over here is easy. Integration over here is easy. Whereas integration over here becomes more complicated because the 2 parameters are related by this slope. Although I can parameterize it, I have taught you how to parameterize it. Yeah, so that becomes quite complicated. Yeah, because over here you have to deal with exponential function and cosine functions. So integration by parts comes in, right? Remember, yeah? So whenever you have a trigo function, exponential function, you always have to do the integration by parts, even though there's a x parameterized in terms of t, y parameterized in terms of t. You have this problem of exponential function multiplied by trigo functions. You always have to do integration by parts, and that is a problem with many of you, I know. Okay, so what you do is, right, integrations over this closed contour now. What is the answer? Must be equal to what? 0. Why? Because this function f here is analytic in any closed contour that you can think of, and this is one of them. Yeah, so this integration can be broken into the sum of these 3 integrations, and it must be equal to 0. And what you wanted is what? You only wanted this term, right? You wanted over this, only this term. So you bring the other 2 terms to the right hand side. So I do the integration over here, C1, I do the integration over C3. You add it up, and the negative of it will give you the integration over C2. Right? So this question, in fact, is very good. Yeah, I like this question. But you have to think. You have to think. Okay, if you want to use a brute force to integrate it over a straight line, then for this particular problem, you may get stuck because you need to integrate by parts. Yeah, so there is a reason why they use the word hence. Yeah, hence. Okay? There is always this trick that you need to know about the exam. So any queries on this part? Okay. Anyone, any query? Okay, if not, let us move on. Okay, over here, there's another one on checking about continuity of this function. Yeah, at a particular point, and then you also ask to comment on differentiability and analyticity. Yeah, so always remember we check differentiability first. Differentiability first, then we talk about analyticity. Yeah, and the whole idea is to make use of the Cauchy-Riemann equation, CR equation. And CR equation is only used to check differentiability, the conditions under which it's differentiable. Only then you check whether it is also analytic. All right. And this one here, of course, it is the contour integrations, right? And here the path here is what? Contour is what? Closed, right? It is a circular path. It is a circular path. And counterclockwise important, yeah? CIF, the result given with the formula here is only for counterclockwise contour, yeah? So, yeah, this is your complex function e to the power iz. So to check limit, what do? Again, you will need to decide how to represent your z, right? And this function, exponential function, so clearly representation of z by polar form is out. So the only thing is to represent your z by x plus iy. X plus iy. Yeah? Represents your z by x plus iy. Now you want to check the limit when z tends to 2. So this is your z naught, right? So to check the limit, you need to replace all the z by what? Z naught plus z, right? With the z represented by x plus iy. You shift the origin to z naught. Shift the origin to z naught. Yeah? And then at the same time, I'm going to, well, this is a point 2, yeah? I want to approach from these directions, y equal to kx. Y equal to kx. I choose this direction of approach to this z naught here. Z naught is equal to 2, yeah? Okay? So the x and y are shifted with this z naught as the origin now. Okay? Right. So instead of doing this limit here, which is tough to do, I change now. I replace all the z by what? Z naught plus z. And I replace the z by x plus iy. And then I replace the y by kx. And I take the limit as x tends to 0. Because if I do that, right, when x tends to 0, y will also tend to 0 because y equal to kx. K is just a constant value. It could be very, very large. But when x tends to 0, y also tend to 0. Yeah. So x tends to 0, y also tend to 0. Then you approach this point. Z naught. Right. So this concept must be understood. Yeah. I want to approach this Z naught. So I approach it from this direction. Okay. So replace this function here by this one here. This is how the f of this whole thing here is defined, right? So replacing all the z by this. So in this case now I can only take the limit as x tends to 0. X tends to 0. So limit with respect to only one parameter. I don't have to look at the y because y is already taken care of by this kx here. Okay. So what happened when x tends to 0? X tends to 0. This go to 0. This go to 0. Then what happened? This one, then what happened? Anyone? What happened? This one here will approach what? E to the power of I2, right? With no difficulty. E to the power I2. So now, e to the power I2. Does it contain the k term? No, no k term. So it's independent of the direction where I approach. Z naught. Because k here, as you can see, this is a slope, right? This is a slope that I approach. this point here. So this indicates the directions of approach. Directions of approach. So now this limit here, if you put in the x equal to 0, so this term disappear, that term disappear, it only becomes I to x. So this is something that you have to do the conclusion yourself. Yeah, I to x. E to the power I to x. So k term doesn't appear here because as I approach this x equal to 0, this disappear, that disappear, so the k term also disappear. So the limit is independent of k. Independent of k means independent of the direction where I approach that knot. So the limit is unique. So your thought has to be very clear, yeah? The limit is fixed, a constant, independent of k, so it independent of the direction where I approach the point of interest. So the limit is unique. If the limit is unique, then the limit exists at this point. Yeah? So the next thing is to find differentiability. So to find differentiability, this exponential function, so z again should not be represented by polar form. The only thing is to represent it by the rectangular form, x plus iy. So replace the z by x plus iy, then this complex function becomes this. And I want to extract out the real part, extract out the imaginary part. So here is e to the power x minus y. So e minus y taken out here, this is completely real, right? Then we left with e ix. Basically, e ix times x plus iy will be equal to e to the power of, no x here, right? Only I. Yeah. Yeah. So this one here, e I x plus iy is equal to e minus y plus ix, right? So this is equal to e to the power minus y times e to the power of ix, right? I hope you understand how to manipulate this complex number, yeah? So this is already the real part, but this one here, I don't know. So this is a polar representation, so I need to come up with the rectangular representation. Okay, so this is the rectangular representation of e to the power ix. So I multiply this into here to give me the real part. This multiply into sine x to give me the imaginary part. Okay, so you have u and v now. Then again, you have to come up with 4 partial derivative, right? Ux, vx, uy, vy, and then you establish the cross term equality. Of course, one of them have to change to a minus sign, and that will give you the 2CR equation. And there is no need for you to remember the formula, right? Given in the appendix, like the case of the quiz. So you check the condition under which the CR equations are satisfied. And it turns out that CR equations are satisfied for all x and y. So if satisfied for all x and y, it must be differentiable for all x and y. So it is differentiable everywhere. Differentiable everywhere. So it is differentiable everywhere. It must be analytic everywhere. All right. Right. So the last few steps, I want you to think about it. Yeah. You really think about it. I'm not going to give the complete answer. Okay. You have to try it out. I don't have the complete answer anyway, because I'm not set any of this question. Yeah. So now I have to deal with this complex number for this question now. Right. This part, I need to integrate this complex function. Right. Over the closed contour. This is closed contour. Okay. So first of all, I need to be able to identify the roots of the denominator. I'm interested in the case where the denominator go to 0. Where the denominator go to 0. This term here is easy. Still stay put here. But this term, I need to complete the square, right? Complete the square. So by completing the square, I will get this as the 2 roots. This one here will give you the roots at +1. This one here, okay, will give me the 2 roots at +1, plus and minus 2i or i2. Yeah. So altogether, there are 4 singular points. 4 singular points. Okay. So Now, then what you need to do is what? Draw the closed contour that is of interest to you. This contour has a center at where? At where? 1 plus I, right? So look carefully. This one here means a circular region with the center is at 1 plus I, and the radius is 2. Radius is 2. Okay, so I draw a circular region, center at here, radius 2. Radius is 2. Then drawing it properly, then I will be able to tell the 4 singular points, 1, 2, 3, 4. This is repeated here, whether they are inside this contour or not. And this is counterclockwise, yeah, counterclockwise. So since the radius is 2, so from here to here must be magnitude 2. But this is 1, this is 2. So this one here must be inside the closed contour. And from here to here is only unit the magnitude of 1. Yeah, from here to here is 2. And this is minus 2 here. So from here to here is 2. From here to here is 1. So this point here must be outside the closed contour. So only 3 singular points are inside the closed contour. Only 3 singular points are inside the closed contour. But this one is outside. So what you do is to change the integration differently now, right? So this integration is changed into how many integration? 2 integrations. And the contour, is it the same? No more, right? No more the same. I now change the contour here into multiply connected region. Multiply connected region, yeah? So one of them is C1. C1 contains the singular point of +1. So make sure your notation is correct, yeah? You cannot say C and this replaced by C again. Then your answer is wrong, in fact. Okay? So this part, and then plus another one, the other singular point here, this point here, I want to retain this factor in the denominator that describe this singular point. And then all the remaining term, or this one here, all the remaining term grouped together. So this one here is already in the denominator. So the remaining term is over here, right? So I put them in the numerator here. Okay. So likewise over here, I need to factorize it. I retain one of them in the denominator. The other one is this term here. This times this times this will give you z squared minus 2z plus 5. Right? So I retain one of them in the denominator because this is the singular point. This will give me the singular point. This one here inside the closed contour. Whereas other singular point also over here is outside the contour. So I group it together with this remainder function, z over this, right? Okay. So very clear that you need to define C1 and C2. C1 includes only the singular point at +1. C2 includes only the singular point at +1 plus I2. Right? So this singular point is of order 1, simple singular point. This one is of order 2. Right? It's repeated. Then with this form, you can now apply CIF to this. But when you apply CIF to this, be careful here. This one is repeated singular point. So you have to differentiate this, the numerator. You have to differentiate the numerator once and then evaluate it at that singular point. Whereas over here, you don't have to. It's a simple singular point. So you simply evaluate the value of this function in the numerator at the singular point here. Yeah, at the singular point of +1 plus I2. Okay. So any queries? Okay, if not, let us move on. This one here, as I said, this one can be done much easier using the concept of integrations of the derivative of a function divided by the function. And you will get tangent of that function. Yeah, that function is the denominator function. Okay, I'm sure many of you forgotten about it. So it doesn't matter. I'm going to apply the new tool that I've just learned. I'm going to convert this into contour integration. Look carefully here. This is integrating from 0 to pi. So it does not give you one whole circle. Does not give you one whole circle. So I cannot come up with a closed contour. But then I look inside here. This is 2 theta. This is 2 theta. So if theta go from 0 to pi, 2 theta will go from 0 to 2 pi, right? So I would have this integration from 0 to 2 pi. So all I need to do is to change a variable. I define alpha to be 2 theta, alpha to be 2 theta. So let us see. So if I let alpha to be 2 theta, then the integration will change in terms of integration with respect to alpha now. Right? With respect to alpha, instead of 2 theta, I have alpha here. Right? So theta go from 0 to pi, alpha go from 0 to 2 pi. Then the next thing that you have to worry about, if this is this one here, then d alpha equal to 2 d theta. So that implies that d theta is equal to half of d alpha, right? So I need to replace the d theta by this. So now I have integration from 0 to 2 pi. So this is where I can construct a circular region. And the standard trick is only to use a unit circle. Good enough. I don't have to decide on what is the value R. R is just one. And that's the reason why I let Z equal to 1 times e to the power I alpha. Because from here, then I use the Euler's formula. I will get sine alpha, cosine alpha, because this one equal to what? Cosine of alpha plus I sine of alpha. Yeah. And then I need to create another term, which is the inverse of Z, which is equal to cosine alpha minus I sine alpha. Okay. So adding this Z and Z minus 1 will give me 2 cosine alpha. So cosine alpha becomes Z plus Z inverse divided by 2. And to get the sine alpha, I have Z minus Z inverse. Z minus Z inverse, I will get 2i times sine alpha. So sine alpha becomes Z minus Z inverse divided by 2i. Okay. Then the next thing that you need to do is to come up with dz, because I'm going to do complex integration. I need to have the dz. So from here, you differentiate it with respect to alpha. So I get dz on the left-hand side. On the right-hand side, you differentiate it with respect to alpha. I will get, right, the constant I times ei alpha times d alpha, right? Because dz d alpha is equal to I times e to the power I alpha. Okay, but what is ei alpha? Ei alpha is your z, right? We have set it to be equal to z. So reorganize this, then d alpha will be changed into dz over iz. Dz over iz. And because of choice of this z here, now as alpha go from 0 to 2 pi, I will now have this closed contour, which is a unit circle center at the origin. Unit circle center at the origin. Okay, so when that is done, now I will change this one here into closed contour integration now. So no longer this integration, I change it to this integration over the closed contour. And this closed contour is your, this one here with the C inside here, yeah? Hey, how come the eraser function disappeared? Funny. Hey, eraser function disappeared. Okay, never mind. All right. So this is what I will get. So change into this sine alpha, change to this term here. Right, I derived earlier on. And then cosine alpha, change to this term. And then d alpha, change to this term. So it looks very complicated, but you can see simply you cancel off these two with these two here, but there's still an I inside here. If you cancel off here, bear in mind this must be multiplied by 2, right? So that these two cancel with this, multiply into here. And these two will cancel out. So simplifying this one here, including this iz here, I would have this function. I would have this function, right? I would have this function. So now the key thing is I need to know when this function here go to infinity. I want to know the singular points of this function. So I can only look for it in the denominator. And of course, this z here, one of them is obvious. Then these two here, I need to factorize it. If I factorize it, I get the two roots. One is minus 2 minus square root 3. The other one is minus 2 plus square root 3. Yeah? and this factor half is still there. So now, out of the three singular points at the origin, at -2 minus square root 3, at -2 plus square root 3, which are the one that is inside the unit circle? Which are the one that is inside the unit circle? Of course, this one here, the roots at the origin inside the unit circle, right? This one here, the roots is at -2 minus square root 3, of course, outside the unit circle. But this one, is it inside the unit circle? So look, -2 plus square root 3, square root 3 is approximately 1.7, right? So 2 minus 1.7 is 0.3. So the singular point will be inside the unit circle. Okay, so this one here, same as earlier on. I would now consider two singular points. One of them is at the origin. So in this case, I need to retain this z in the denominator. The rest, including 2 in the denominator here, everything including the minus sign, must appear in this numerator. Yeah, appear in this numerator. And I integrate it over a different contour now. This contour C1 includes only the origin as your singular point. It should not include the other singular point there. Right? So it's a very small contour surrounding the origin. How it's being defined? Irrelevant, as long as it includes only that singular point. And then I also need to take care of this factor, because this factor here will give you the singular point inside the unit circle as well. So I need to define another contour, C2. So I will retain this factor in the denominator. Then the rest, including the factor of 2 here and the minus sign, everything will be retained in the numerator. Then you apply the CIF to this integration, apply the CIF to this integration, and add the two together to give you the final result. All right. Okay, so for this one, I go to slight more detail because in the quiz, especially in the makeup quiz, some of you have to face this integration here. So many of them don't know how to do it properly. Yeah. Now for the quiz, for most of you, you have this kind of integration, okay? Indefinite integral from minus infinity to plus infinity. Right? So again, if you look at real integration, this is very tough nut to crack. You need to remember all the special formula related to trigonometry in order to solve this. So again, we will use a new tool now. We will convert this into complex integration. So instead of doing this indefinite integral, I'm going to use the complex integration over a closed contour. So the best way to resemble this indefinite integral is to use the upper half plane. Why upper half plane? Because I want to have the counterclockwise encirclement. Yeah, counterclockwise contour. Right. So this one. Now be careful. Change the notation. Yeah, this is real integration. I now change it into complex integrations. So the variable x change into the variable z. Yeah, variable x change to variable z. So this one here no change. Just change the symbol, including dx become dz. But this integration very important. Yeah, change to this integration now over the upper half plane. Okay, so now the issue is I want to find the value of z where this is 0, because that will give me the singular point of this whole function. So first of all, I complete the square, I will get this. Yeah, so I will get two factors. I will get two factors. Right, I will get two factors here. Right, one is this, the other one is this. So check, this singular point will be at where? At +1 minus I square root 2. This one here will give me the singular point at +1 plus j, already I or j, yeah, j square root 2, yeah. So which is the one that is in the upper half plane? The roots from this factor here will give me the roots in the upper half plane. So I want to retain this factor in the denominator. I want to retain it in the denominator. Then the rest, I will group them together and put it into the numerator. But my this square also apply to here, right? Square also apply to here. So I have to put the square term there. Don't forget that. Many of you are quite careless, yeah? Because this whole term is squared, right? Here, this whole term is squared. So these two, power 2 here also apply to this one. So this term here is the power 2. So now, this is the standard form that we can apply the CIF. But be careful when you apply CIF, bear in mind the singular point is not simple, it is of second order, So I will need to differentiate this function. I need to differentiate this function. So bear in mind when you differentiate this function here, be very careful, yeah? You must differentiate it properly. If you're not very sure, go back and revise through how to differentiate a function of this type, which is a quotient of two functions. Yeah, quotient of two functions. Yeah. So you use a quotient rule. Yeah, to do this differentiation. And you differentiate only once because this is of second order. And then put in the value of the derivative evaluated at those singular point and multiply by 2 pi I. And then finally, the answer must be real. If you get a complex answer, you know you either make a small silly mistake or your whole concept is wrong. And the same thing applies to this. If you evaluate it, these two here must be giving you only the real answer. If the answer is complex or imaginary, then you know you are making some mistakes along the way or you have a wrong understanding. Yeah. So it is a very easy check. Yeah, for this kind of integration. You're expecting a real answer. Of course, when you get a real answer, doesn't mean the answer is correct. Yeah. Okay. I do this kind of reorganization because this is the only one that represents the singular points in the upper half plane. Yeah, upper half plane. Okay. Then this. This is in fact the chain rule, but the vector version. Yeah, chain rule and the vector version. Very seldom we come up with this kind of more theoretical derivation. Yeah, but this year, bear in mind, this year the one who said the exam question is quite different. Yeah, so I don't know. He may have more inclination to prove certain kinds of result. So for this one here, it looks easy, but you have to be very careful. Yeah, you have to be very careful. So what you do is think of this as a function which is a product of two functions here, and you take the cross product of these two. Yeah, take the cross product of these two. All right. So cross product, right? So this the notational vector. The second row comes from the components of this. The third row comes from the components of this. F times V1, F times V2, F times V3. Right? F is a function of X, Y, Z. V1 also function X, Y, Z. Likewise over here, right? F function F, X, Y, Z. V2 also function X, Y, Z, and so on. So this one here is the product of two functions. Product two function. So if I apply this operator onto here, you have to apply the chain rule. Likewise, apply this one operator onto here, you have to apply the chain rule. Yeah, and so on. So I hope you still remember how to compute this determinant that give you the cross product. So we always expand along the first row, right? Always expand along the first row. And then you compute the component in X, component in Y, component in Z. Yeah, individually. The only thing is when you compute the components in the Y directions, be very careful. This one is associated with a minus sign. That's the way you compute, so-called the determinant of the 2 by 2 matrix. You have to compute the negative of the determinant. Okay, so you do that, you get this. So the key thing is, now I need to apply this operator onto this function here. This one is a product of two functions, both of them involving functions of X, Y, Z. Involving function X, Y, Z. So to differentiate this, I invoke the quotient rule. This one also invoke the quotient rule, and so on, right? So if I do that, right, then I need to reorganize the term. So differentiate this with respect to what? To V3 first. So F times differentiation with respect to V3. And then this term here will be combined with this term that give you the quotient rule. Right? But I shift this onto this one here. There's a reason to that. Then if I differentiate this with the minus sign, this one with the quotient rule will give you this one plus this one. But because of minus sign, this becomes change to minus, this to minus. So I shift one of the term to here, whereas the other term shift it ahead of this. There's a reason for that. Because this one here give you something that you wanted, and this one here give you something that you wanted later on. Okay, and applies to the others as well. So I do a shifting. So if you look carefully, what is system? And what is system? You look at the result on the right hand side, it will tell you exactly why you do that. Look, this is F, right? F. So these two terms here, there's a common term of F that can be taken out. So you take it out here, these two together will then give you the F times dV3 dy minus dV2 dz. Yeah, and of course these two terms here, what is something common that you are looking for also? So I will leave you to figure that out. Yeah. Okay. So the rest all the term, and then in fact with that you will then construct this term, right? Remember there's a cross product. There's a difference of the two differentiator. This is a common F here, and then the other one will be a part of components of this. And then the other one is the simply cross product of these two here. There's a V, right? There's a V. Yeah, there's a V. Looks like there's a V here, V3, V2. So this comes from the components of that V. So there's a reason why I reorganize it. And then if you look at it carefully, in fact, you will recover exactly what you expected on the right-hand side. Yeah. So this one here looks easy, but you need to know exactly what you are doing, yeah, in order to come up with the equality on the right-hand side. So this kind of proof is not for everyone. You have to know your stuff. Yeah, you really have to know your stuff. But the basic stuff is in fact the quotient rule. But you have to reorganize the terms so that you recover the vector form. Okay. Next is this vector calculus now. Right. So you are going to compute this one here. This one is what? To calculate the work done, right? The force that you encounter as you travel along this contour. So this integration will give you the work done. Yeah. So this vector field, the force field is given, and the contour is a straight line contour. Straight line contour, right? From this initial point to this final point. So do you know how to parameterize a straight line contour? Can, right? This is a starting point. This is a ending point. So the directional vector that you need to have is the initial point plus t times the final point minus the initial point. And then simplify it, you get the reparameterizations of this directional vector into a vector that depends only on one parameter t rather than simply x, y, z. Okay, and then f also will be changed because you are restricting it to this contour, and since this contour is parameterized with respect to one parameter, the f will also be dependent only on that parameter. So this integration becomes something simpler now. Instead of dealing with three independent variables of x, y, z, you have only one parameter in this integration. Okay, and then over here, this is the curve, right? So you are going to use the spherical surface parameterization. So you are supposed to use surface integration for this one here. Okay, so let us look at the surface. This one here, this is the surface, clearly hemispherical surface, and x greater or equal to 0. X greater or equal to 0. Right? So in this case, it is an open surface. An open surface, only the top hemisphere. And the vector field is given. Yeah? So you need to compute the curve, because if you want to compute the flux, you have to compute the curve. Yeah? So straight line from this point to this point here, and this is how we parameterize it, right? I've told you, right? This is the general directional vector, which is x, y, z. I'm going to parameterize it in terms of V1, where V1 initial point, plus t times V2 minus V1. And t, in this case, t will change from 0 to 1. T varies from 0 to 1. So simplify this, add this to this one here, I will get this vector. So clearly, instead of depending on x, y, z, I depends on t only now. So only one parameter. The next thing that you need to do is to differentiate this r with respect to t, right? Because I need to replace the dr by this vector. Okay? So the rest, I'm sure you know what to do already, right? We have done a few examples on this. So the meeting, I want to emphasize again the parameterization of a straight line. So this formula is extremely good. Yeah, extremely good. Okay. So now here, the second part, this is the surface. The surface here, right? The surface, this is hemispherical surface, and you restrict it to the case where x is greater or equal to 0. And look, which table are you looking at? Which table are you looking at? You are looking at the YZ table, right? X is positive only. X is positive. So think of the cake sitting on the YZ table. But this is not complete cake. I only look at the surface. Only look at the surface. Yeah, look at the surface. Okay. So in this case, the directional vector always parameterized in terms of these two this way. Okay, in terms of this way. So V is the angle between the directional vector and the z-axis. Yeah, and U is the angle after projecting down onto the xy plane, and the projected this vector here, the angle that it makes with respect to the x-axis is called the U. So now you want to change the U and V so that this tip here will sweep this hemisphere, So in this case, how should you determine the range of U and V? So clearly in this way, you draw the diagram. That's why it's important that you need to know to visualize it so that you can determine the value of U and V. So clearly, if you look at V here, starting from this point, you sweep until down here, right? Sweep down here. So V will go from 0 to pi. V will go from 0 to pi. Yeah? So this one, not too bad. Not too difficult to understand. And then what happened to U? U go from 0 to pi over 2? Cannot be. Cannot be. So U here will have to start from the negative y-axis, which is this point here, right? Negative y-axis is here. I start from this point here. Okay, this point here. At this point, what's U? U is minus pi over 2. U is minus pi over 2. So as you sweep from minus pi over 2 to pi over 2, you get this point. Okay, sweep from here. So think of this as a negative real axis here. So this point here is when U is minus pi over 2. And this point here is U when it's equal to pi over 2. So that's why U, the range is from minus pi over 2 to pi over 2. We have looked at the case where the cake is sitting on the XY table, right? There's one way to, a different way of deciding on the range for U and V. Then there is another cake, which is the XZ table. XZ table. So I will leave it to you to figure out what is the range for U and V, while keeping these parameterizations of the directional vector in terms of the U and V only. So this one here becomes less headache. Yeah, less headache. Once you understand this, apply it to all the three cases of hemisphere. Yeah. So once you get the directional vector, I need to get the normal to the surface. So I need to differentiate R with respect to U first. You get this vector. I need to differentiate R with respect to V. I will get this vector. And then take the cross product of these two. I will get the normal to the surface. Yeah. And then I change the integrations into surface integration now over this rectangular region. This is the new rectangular region. Yeah, this is the new rectangular region. So the integration with respect to R now, right? So the curl here, the curl of F is only in terms of U and V, and then you have to multiply by what? The dA is the normal that you computed. You need to identify which normal that you use. And then times du, dv. Yeah, the normal could also be a function of U and V, yeah? Generally, it could be a function of U and V. And then you can start to do double integration. And this is over a rectangular region, which is not too bad. So generally, this function here, include this and multiply together, will give you a function which is separable. If it is not separable, then you are going to have a hard time. and typically indicates that you're working or strong or you had a wrong understanding earlier on. You must get something that can be separated so they can do two separate integration. Yeah. Okay.
Prof.
Yes.
I don't understand how you decide like when it's x more than 0. Like, how you know it's open?
Come again.
How you know it's open surface?
This is open surface. You're going to surface integration. You're going to do surface integration. Yeah.
How you know it's
so you restrict yourself to the case here. Look at the question here. Okay. Use a suitable spherical surface parameterization. Evaluate this integration here for the surface. For the surface. Yeah. Ranging from x greater or equal to 0.
How you know it's open?
Now, if it's closed surface, you will specify that this is bounded. This one here surface is bounded by another one. For example, it will be specified that it's bounded by something here, your YZ plane. In this case, it will be bounded by YZ plane, then this surface is closed. All right?
Then
like the one that we discussed in the tutorial, remember? The one sitting on the XY table. So it's bounded by the XY plane, right? This one, there's no mention about that.
Then the other question, how you know the range for T?
Come again?
How you know the range for T? How do you know?
Range for T, what do you mean?
0, T is less than 0.
V equal to between 0 and pi. Why? I already explained to you, right? This V here.
T.
Huh?
T.
T.
Yeah.
T varies from 0 to 1. T varies from 0 to 1. I've explained that. I don't know whether you attended my tutorial. I've explained that this is one of the very powerful way to generalize the parameterization of a straight line to go from the initial point V1 to the final point V2. Yeah, I have specifically discussed this in the tutorials. All right. So this concept is the same as what I have done when I parameterize a straight line contour in the complex plane. Same concept. All right.
It's always 1, is it? 0 to 1.
Always 0 to 1 if you parameterize and now V1 plus T times V2 minus V1. The alternative is if you parameterize then so this one V2 plus T times V1 minus V2, then T will change from 1 to 0. From 1 to 0. Okay. So see, this is the problem if you don't attend my tutorial and now you ask me to go over again. Yeah. You can verify with your classmate. I'm sure they will agree with me that I've gone through it in the tutorial, right? Okay. Next, to find the work done in moving the particles along this path here, right? Along this path. This path is a straight line path. Not so, right? Not so. Okay. So from the case where now there's a relationship between X and Y, right? X and Y. Z is 0. Z is 0, but there's a relationship between X and Y, and it is related in a complicated manner. And the range for Y go from 0 to 2 pi. Yeah, from 0 to 2 pi. But in this case, it's a smooth contour. It is a smooth contour. Yeah, a smooth contour. Okay, and Z is 0. All right, and given this force field, and then over here, you're going to do these integrations of the F over this surface. What is this surface here? This surface is what surface here? Cylindrical surface, right? Cylindrical surface. Okay, so let us see, yeah? So over here, this is a smooth contour. So the the directional vector is a directional vector that points from the origin to a point on the contour. Okay, and you're told that Z is 0, so replace the Z by 0 always. Yeah. And X is related to Y. So I'm going to parameterize the Y by theta. I'm going to parameterize the Y by theta. Only one parameter is required. Yeah. Because I'm told that Y go from 0 to 2 pi. So theta also go from 0 to 2 pi. So if I replace y by theta, x will be changed into cosine theta. So now instead of two parameters of x and y, because z is 0, I have only one parameter theta, except that this is cosine theta, this is theta. So related in a more complicated way, that's all. So this is now a straight line that go from 0 to 2 pi. Straight line. So I changed from a difficult contour integration into a straight line integration. Right? So I need to come up with a differential change in the directional vector. Right, differentiate this r with respect to theta. So dr d theta is given by this vector. So dr is this vector times d theta. This is a vector, yeah. And d theta is a scalar. Okay. So with that, I'm sure you know what to do, right? How to do the integration. And your f, you also need to change your f because you're only concerned about the f that you need to overcome as you travel along that contour. So all the x in the f will be replaced by this, all the y in the f will be replaced by theta, and all the z in the f will be replaced by 0. So the f also depends only on one parameter theta. Then you take the cross product, you get only a function which is quite complicated because you have a cosine function theta here. Yeah, but it only depends on the theta. So you can still do integration. Not too bad. Yeah. So I'll leave that to you to work it out. Right. Main thing is understand the concept. So this is the surface. What's this surface here? Okay. This. Right. This is a surface. So this is a parabola. X is z squared. Right. This direction here is z. X. This one here is z. So x. Right. Over here, this is parabola. And when x is 0, this is a parabola. Right. Think of this as a y, x, right? Parabola. Y. X equal to y squared, you get this parabola. Okay. Now along the y directions, it ranges from 0 to 2. Range from 0 to 2. Yeah. And this one here, parabola, is chopped off. You limit it to the case where maximum x is +1. The other one, the z is -1. So this one here, as I said, for this kind of problem, you need to know how to visualize the surface. You need to know how to visualize the surface. So it is an open surface, clearly. Open surface. Okay, so now I need to parameterize the directional vector that points from the origin to a point on the surface. To a point on the surface. So this is the directional vector. So to describe this surface, I need two parameters. I need these two parameters. So from here, I will now define two parameters. One of them is clearly your what? Y, right? This is in terms of y, so I must have parameterized this in terms of y. Okay, so this is the general directional vector. So I use one of them to describe my v. And v go from 0 to 2 as well. Right? I replace the y by this new parameter v now. So v also restricted between 0 and 2 because y changed from 0 to 2. Then the other one, from this function here, clearly I will set my z to be u. Set my z to be u, the other parameter. And this parameter is the case where z is limited to be -1 to 1. So u must also be limited to between -1 and 1. And then your x becomes z squared, which is u squared. So instead of 3 parameters here, I have only 2 parameters. So I need to have the normal to the surface. How to compute the normal? I need to differentiate r with respect to u. I need to differentiate r with respect to v. Then take the cross product of these two vectors. I will get a normal to the surface, and it clearly depending on u also. Yeah. So I need to know where is that normal. So depending on the equation that is presented to you, you then decide on which is the normal, and then you can then integrate it over the surface. And this integration now becomes simpler because this is now a simple rectangular region. Rectangular region. Okay, so typically the function that you have involving u and v, and it is separable. So you can integrate with respect to u and then integrate with respect to v, each one according to the range of v and the other one according to the range of u. Okay, so the rest, I'm sure your memory is still fresh. For those who have attended my tutorial classes, just follow the same procedure that I've done, yeah, except for a different surface now. Okay, so surface integration is slightly more complicated. Yeah, out of 3 cases, integration over a contour, no problem now, I believe. Integration over a surface, more complicated. Integration over a volume, in most cases, the problem setting becomes quite simple. In most cases, yeah. So over here, this one, quite a recent one, yeah. Quite a recent one. So you are now looking at this scalar function, right? Scalar field given by this. You are asked to find the directional derivative, yeah, at the origin, but in the direction of minus phi I. So this is where the lecturer will catch you in this direction here. So you want to find the unit vector representing this direction, right? Unit vector representing this direction, very important. So after you are getting the derivative, you take the dot product with respect to the unit vector representing this one here, which is minus 5i divided by the norm of 5i, right? Which is equal to what? Minus I, right? Minus I. Okay. So this is the force field, right? And you're asked to show whether it's a conservative or not. Then what you do is you want to get the work done. So over here, if you were to do a direct integration from this point to this point here, again, you are going to have a slight difficulty because the function that you have here are quite complicated, x squared, z cubed, and so on. So this integration, even though you can parameterize the straight line contour, depending on one parameter, so this becomes quite a complicated function. Yeah, you can do that. So the alternative is to construct the scalar field representing this vector field. Yeah, we have discussed this in the tutorial, right? So this kind of question is quite popular in exams, yeah, come up quite regularly. Not every time, but almost every other semester you will have something like that. Okay, then finally, you find the outward flux of this vector field across the surface of the hemisphere, across the surface of this hemisphere. Okay, so first part given by this. Right, so what do we need to do? Right, we need to find the directional vector, right? So first of all, I need to find the derivative first. So apply the del operator onto this, I will get this. Okay, so the directional vector with respect to this direction, bear in mind, this is the unit normal representing the direction of minus 5i, right? Unit vector, very important, yeah? It's not the dot product of this derivative with minus phi. No, wrong. Because in this case, you will scale the magnitude of the derivative. You must come up with a unit normal, rather unit vector representing the directions of interest. So take the dot product of these two, which is in fact essentially minus I, right? Then you will get certain value, yeah? When you get that value, it will be a function of x, y, and z. So put in the value of x, y, z is 0, 0, 0 because at the origin, then you will get the directional vector at that particular point. And this part is something new. You have not discussed it, but once you understand the concept, this is already the derivative, right? You are interested in the derivative, the case of derivative when it is equal to 0. You are interested in the case when the derivative is 0. So you set this to 0, a 0 vector, right? This is a vector, so set it to a 0 vector. So when this happened when this is 0, this is 0, this is 0. So you get 3 equations, right? Set this to 0, set this to 0, set this to 0, and you need to solve for x, y, z. The point in the 3D world where the derivative is 0. So 3 equations, 3 unknowns. You can solve it using linear algebra, right? Instead of 3 equations, 3 unknowns, in fact, you solve for z straight away. From here, set this to 0, you solve for z straight away. And then you have only to deal with 2 equations with 2 unknown x and y. When you set them to 0. So you straight away compute the value of z when this is 0. And then from these 2 here, you compute the value of x and y when these 2 are also 0. So just apply the concept that you have learned in linear algebra to decide on what is the value of x, y, z when this derivative here, the whole derivative is equal to 0. Right? So it's something new that we have not seen in the tutorial, but just apply the concept correctly. Okay, this is the derivative, and I want the derivative to be 0. There is no change in the the scalar field. And I want to find the point in this 3D space. I want to find all the points in the 3D space where there is no derivative. Yeah, the scalar field is fixed, no change in that scalar field. So now, given this vector field given by this, right, I want to show that it's conservative. So I apply the del operator onto this vector field, right? So I take the cross product. Take the cross product. So you ask to show that it's 0. Yeah. And of course, you can show that this is equal to 0. Yeah. You just have to apply the cross product, the formula that I have mentioned many times. Okay. So now what I wanted to do is to recover the scalar field. I want to recover the scalar field V. The vector field is given, right? So if I have this scalar field, if I differentiate it with respect to x, I will get the x components of this vector field, right? Which is this. And if I differentiate the same V by V here, same V by V, I will get the y components of this vector field, right? If I differentiate the same V again with respect to Z, I will get the components of this vector field in your Z direction is this. So over here, I have 3 first order derivative, and I want to recover my V. I want to get my V. So for this one here, to get the V, I integrate both of this one here with respect to what? X. With respect to X. So if you integrate this one with respect to X, I will get the V. Integrate this with respect to X, I will get this. Plus a constant. But this constant is a constant with respect to X. Very important to understand this. Don't just put a constant here. That's wrong straight away. It is a constant with respect to X because you're integrating with respect to X on the left-hand side. So you will get a function here which could depend on X and Y. Which could depend on X and Y. It cannot be just a pure constant. So likewise over here, if you integrate on both sides, on the left-hand side, integrate with respect to Y, I get this. Integrate this with respect to Y, I will get this as well. And over here, there is another function which is a constant with respect to Y, but it can be dependent on X and Z. Yeah, X and Z. Then over here, if I integrate it with respect to Z, on the left-hand side, I will get the V. And over here, integration with respect to Z, I will get this function here. So I get 3 different V. 3 different V. And they look different. Although this term and this one are the same, but here they are different. So I need to look for the common term, right? Look for the common term. Where's the common term? The common term is this here, this, and this. So this must appear in the final form of V for sure. Final form of V. So I need to find the common term. If some of them is missing, I need to recover it from so-called this function here, which represents a constant with respect to Y. This is a constant function. This is a function constant with respect to Z. Depends on X and Y. But there is no need to. All these 3 appears in the V. So just nice. So the V must be this one. Right? Must be this one here, appear inside the final form. Is that all? Not true, right? How about here? This, and this. So I need to add in a constant C here. So these 3 here function are in fact a big constant. Constant with respect to X, constant with respect to Y, constant with respect to Z. Okay, so you will get your V. Okay, so once you recover the scalar field, then computing the work done is very straightforward. It's simply the value of this scalar function at the final position minus the value of this scalar function at the initial position, and that's our work done. So that becomes easy. But if you want to do a direct integration, you can try it. You know how to parameterize a straight line contour. You integrate over this straight line. And of course, in this case, integration is more complicated because of the fact that the function here is quite complicated. Yeah. This function here is quite complicated. First of all, you need to parameterize the contour first. Yeah. So you have very complicated functions. Okay. So this approach is much easier to use the scalar function, potential field to evaluate the work done, which is the difference of the 2 potentials at 2 different points. And that is independent of the contour that you take. I only worry about the potential at the final point. and minus the potential of the initial point. Okay, this one again is the open surface, right? This is a nice vector field. Okay, so the flux is the integrations of this one here over the open surface. So this dA can be replaced by this or the normal times du dv, whatever the two parameter that you want. Yeah. So for the case of hemispherical surface, the normal to the surface is always what? This directional vector. Because this one here is what? This force field tend to be the directional vector also, right? X, Y, Z. So this is very important understanding, right? So over here, X, Y, Z. So this directional vector, right? So it points this hemispherical surface, for example. So the outward from the origin to here. So this must be my normal, right? Must be like normal, same direction here. And I wanted is only the unit normal. So to get the unit normal, I have this directional vector divided by the magnitude of this directional vector, and that will give me the unit normal straight away. All right. So F dot N here, this is the F, which is R. N is the R divided by the magnitude of R. So the dot product of these two will simply give me this one. Yeah, will simply give me this one because F dot this N here will give you X squared plus Y squared plus Z squared, and then divided by the square root of this, I will get this. And what is this? This is none other than a simple constant. A simple constant. Simple constant. So integrations of this one here becomes what? Right? Over here, F dot N is just a constant A. So I can take it out, left with only one. So I integrate over the area. Integrate over the area of this surface. So A retains. What's the area of this surface? What's the area of this surface? Hemispherical surface. What is the surface area? What is the surface area of the hemisphere? Surface area of the complete sphere is 4 pi a squared, where a is the radius, and I wanted only half of it, so it's 2 pi a squared. Yeah, 2 pi a squared. Yeah, so this is the simplest way, but this one requires you to understand the concept, yeah, of this F dot N. If not, then we will do the usual integrations over the surface. Do the usual integration over the surface. Okay. So in this case, with this parameterization, remember, right? F is still this, right? And then the normal to the surface, the capital N, will be this. The normal to the surface will be this N. Yeah, we have derived it before earlier on. And then times d theta d phi, because I use the theta and phi as my parameter. Okay. Okay. So now this range here, the R is this, right? The range for R is this now. Okay, and use the same directional vector. Okay, so I can use this to do the integration. I should get the same answer. Now, one common mistakes that many students make is think of this as a closed surface, including the bottom. Then they apply the divergence theorem. So I want to calculate the integration over the triple volume. And surprisingly, they get the same answer. They get the same answer. But the understanding is completely wrong. Completely wrong. Okay? Completely wrong, because the surface is open surface. You cannot use the divergence theorem. You get the same answer. Why? Because if you add in the surface at the bottom here, you integrate over the bottom surface, the answer is 0. Why? Because on the XY, on this plane here, what will happen to the normal? What will happen to the normal? Because of this as a vector view, what is the normal? On this surface here, 0. They're all 0. Okay? That's why integration over this surface here is 0. So whether you all integrate over the volume or over the surface for this problem, you get the same answer. But the understanding are completely different. One of them is completely wrong, the one is correct. Yeah? Okay? All right. So this is the alternative. I'm going to think of it as a closed surface. Closed surface. Right. So this is my required result. So I'm going to think of it as a closed surface. The top hemispherical surface. Right. And over here, close it. This is closed surface. Then I need to minus the surface in the bottom here to give me this surface integral. Yeah. Now, this is the closed surface integration now of this whole complete hemisphere. So I can use the divergence theorem on this. I can use the divergence theorem on this, right? Now, the funny thing is this one here, this integration is equal to 0. Right? Because the normal here is here. Right? The normal is this vector pointing in the Z directions, right? Pointing in the Z directions. And over here, what happened on the disk? On the disk here, what happened to the Z? Z is 0, right? So X, Y, Z, Z replaced by 0. So the dot product of these two here will be 0. So integrating 0, you get 0. Integrating this one here, you get 0. So this term here doesn't contribute anything. But it is important that you have to state this. This is 0, otherwise your understanding is wrong. You cannot say this equal to this. Okay, cannot say that. You have to explain that equal to this because this term is 0. Very important understanding. So as an examiner, you grade it according to your understanding. If you don't have this explanation and you say this equal to this, although the numeric answer is correct in this case, but you do not demonstrate a correct understanding of the problem. Okay. Okay. So then how to deal with this closed surface integration? You can then use the divergence. So in this case, what you can do is to compute the divergence of F. And it turned out to be a very simple integration. It turned out to be a very simple integration. It is just a constant, right? Divergence of F will be a constant with this F here, a simple constant. So if you integrate over the volume and the volume of the hemisphere, which is half the answer that you wanted earlier on. Yeah. So that's all for all the problems that I am going to use to illustrate the concept that we have learned. Yeah. So any queries? Okay. If not, that's all. Yeah. Good night. Okay. I wish you good luck in the exam. As I said, I will grade one of the exam questions. So far not decided, but quite likely I will grade the one on the linear algebra. One of them. I don't know which one yet. Okay. So good luck in the exam. Yeah. All right. That's all.
Prof, then for tomorrow's makeup, is
Tomorrow is the same
summary.
thing. So you don't have to
Same
attend
thing,
tomorrow one. It's the same thing.
Okay,
It's the same.
okay.
I want to have 2 classes because I combine the 3 into single one session. Yeah. So I want to give there's some flexibility to y'all. So depending, maybe some of you tonight busy, so you can attend tomorrow. If you are busy tomorrow, you can attend tonight. Yeah. So at least there's this flexibility. The same, yeah, I can promise you exactly the same. I do not have additional slide to show you because to work out all this thing here and with the proper demo takes a lot of time. Okay.
Hello,
Okay,
Prof.
okay. Thank you, Prof.
Yeah.
Tomorrow got 2 matrix.
2 matrix? No, matrix I've done that already in week number 7.
Whoa. Okay.
Yeah, I've done that in week number 7. Remember week 7, there was no proper tutorial. I used that to go through the part of linear algebra. Otherwise, for this whole discussion, I will use 3 hours or more.
Okay, can do brief one.
Okay. No, I cannot. I cannot. I have to go through to take care of the other group.
Okay,
I
no
will go through the
worries.
same thing. No, I cannot. It will take me a lot of time. Because the linear algebra part is a lot of things inside there, yeah? Which I have used, in fact, 1.5 hours to go through that part. So if combined with this, add together, if I go through all over again, it will take me 3 hours.
Okay.
Okay? All right. So I hope you understand. Yeah? I hope you understand. I already put in this additional effort for y'all. If you don't turn up, then there's nothing that I can do. Yeah. Okay. Right.
Thank you,
Good
Prof.
night. Yeah.
Good night.
Good
As
night.
well.
Prof,
Bye
double
bye.
confirm one thing. Exam
Yup.
format is no change, right? It's all about the same format. Question 1, 2,
Yes,
3, 4.
format, I think it's the same. Format is the same.
Okay.
Format
Okay,
is the
thank
same.
you.
So there'll be 2 questions on linear algebra, 1 questions on vector calculus, 1 questions on complex analysis. But sometimes a certain part, it could be require the knowledge of the other part. Yeah. Say for example, just now one of them to find the vector field when the gradient when it's 0, right? When it's a 0 vector. So you have computed the gradient, you set them to 0. So you get 3 linear equations. So you have to solve it using linear algebra, right?
Right.
Yep. Yeah, Daryl, any query from you?
No, Prof.
No, huh? Okay, great. So good night.
Good night. Bye bye.
Good night. Thanks, Prof.